So now let's look at building a multi-layered perceptron to solve the MNIST problem, MNIST classification problem, right? The first step is to initialize a bunch of things, right? So let's go. So in these three lines, as we have seen earlier, we are just importing the data for MNIST, right? So because MNIST data is already available in tensorflow.examples.tutorials.mnist, we're just importing the data here. Okay, and I'm importing TensorFlow here, right? So next step would be I'm just creating a simple code here, and I'm creating a function called plot dynamic, right? Plot dynamic is, so we'll use this plot to eventually plot my epoch on the x-axis and my training and test loss on the y-axis, right? For this problem, we are using the softmax. We're building a softmax classifier, and we have a multi-class log loss or cross entropy, right? So to make this plot, we are actually writing this code, and we are using matplotlib just like every other plot that we've ever used in this course. But we call it a dynamic plot because of a small modification. So because each epoch could take a lot of time, so we will plot as soon as an epoch is over. Let's say I finished one epoch. As soon as this epoch is over, I want to update this plot and make this plot dynamic, right? So maybe the loss is this value at the end of first epoch. At the end of second epoch, the plot is here. So I want this plot to be dynamically updated at the end of each epoch instead of waiting for all the epochs to run, right? That's why we're calling it a dynamic plot, and we call this function plot underscore dynamic. You just have to give this value of what is the loss, both training loss and test loss at the end of each epoch. It will continuously update this plot, right? This is just a plotting function. Next thing. So what is the architecture that we will use? So we are saying that we will have an architecture like this. Our inputs are 784, right? Our inputs, because we have a 28 by 28 pixel image. So number of inputs that we have is 784, right? Because the input image shape is 28 by 28, right? Our first hidden layer we are saying has 512 neurons, okay? And this is fully connected, and this is fully connected. Our next layer, this is my layer 1, my hidden layer 1, right? My hidden layer 2 has 128 neurons and also fully connected from the 512. Finally, I have a softmax layer. Finally, I have a softmax layer that outputs 10 values because it's a 10 class classification problem. So my architecture, if I have to write it simply, is 784 fully connected, 512 fully connected, 128 and 10, right? This is fully connected, this is fully connected, and this is a softmax or a logistic, multi-class logistic. Okay, so this is how I can represent my architecture very, very simply. That's what I'm saying here. My first layer, my input layer has 784. My number of classes equals to 10. My hidden layer 1 has 512 neurons. My hidden layer 2 has 128 neurons. Okay, I'm just defining the network architecture here. That's all I'm doing. Okay, so the next step of the initialization process would be defining some placeholders, right? X is the placeholder to store each of my mini batches, and it's of size 784 and none, right? This is the placeholder that we've seen in the previous video. And y underscore is a placeholder that I will store all of my yi's. Here I store my xi's, here I store my yi's. And I also have two other placeholders called keep prob and keep prob input. So we are using these placeholders whenever we use a dropout. Okay, we'll also show later in this section on using dropouts. And when I have a dropout, right, I need to ensure that given a bunch of neurons, let's assume these are a bunch of neurons and I have these outputs, right? I want to drop out a bunch of them, right? I need to have a vector of numbers, right? I need to have my probability score. Okay, it's just a single value, it's not a vector. So probably I want to use a dropout rate of, let's say, 0.5, right? So keep prob and keep prob input are used as placeholders for dropouts, right? The next thing is I'm going to define my weight initialization. All these are reference links, but we already have gone through Xavier or Glorot normal initialization. We've also seen hay normalization, right? So whenever I'm using simple sigmoidal units, okay. So whenever I'm using simple sigmoidal units, my weights, I'll define them as follows. My weights in hidden layer 1, my weights in hidden layer 2, my weights in the out layer, right? So look at it. From the input layer to hidden layer, this is my H1. My hidden layer to the second hidden layer is H2. To the output layer is out. So all the weights here, all the weights here, all the weights here. We're calling them H1, H2 and out. And I'm defining them to be exactly the same. So my H1 is basically a random normal variable with these many values, right? It's connecting the input to hidden layer 1, right? Right? And what does Glorod normalization say? It says the weights are equal to square root of 2 by fan in plus fan out, and we are adding 1 here just so that the denominator doesn't become 0. Okay, just like a simple Laplace smoothing if you want to think about it. Okay, so when I use this 712, 512, 128, 10 in fan out, for example, for H1, right, this becomes my fan in, this becomes my fan out, and when I replace these numbers, I get a sigma of 0.039, and that's what I'm literally saying here. My H1, right, my H1s, I want them to be random normal with a standard deviation of 0.039. And how did I come to this number 0.039? Because I have 784 as my fan in, 512 as my fan out, and when I do square root of 2 by 784 plus 512, I get 0.039, right? Similarly, my H2, which is connecting my hidden layer 1 and hidden layer 2, again, and these weights underscore SGD are for whenever I'm using a sigmoid unit, whenever I'm using sigmoid activation units, right? This is basically my Xavier or Glorot normal initialization. And we have discussed a lot about Xavier in one of the previous chapters in a video called weight initialization. Similarly, if I'm using ReLU, right? Similarly, if I'm using ReLU units, right? When I use ReLU units, this is how this is ReLU hay normal basically. For ReLU, we use hay initialization, and I'm using the normal, not the uniform initialization there. And this is the variance that you will have, and exactly the same thing. I'm using a random normal, and I just use fan in and don't use fan out, right? And taking my 784, 512, 128, 10 architecture, right? I can always have my fan ins. So here the fan in is going to be 784. Here the fan in is 512. Here the fan in is 128, and so on and so forth. This is how I initialize my weights. I'm also initializing my biases. Okay, I'm initializing my biases to be random normal. Okay, without mentioning anything. So when I say this, what it does is it samples from standard normal, which is normal with a mean of 0 and a standard deviation of 1. Right? So as far as weights are concerned, we are initializing them very carefully using either hay initialization in the case of ReLU or Xavier / Glorot normal initialization in the case of sigmoidal units. Right? Now, there are other things also that we need to initialize. How many training epochs I want to run. Even though we have set this to 15, in lots of real world cases, you might have to run it to maybe 100 epochs or so. So how do you decide till where do you want to run? So basically you have this plot, right, with epoch on the x-axis and train and test loss on the y-axis. So you keep running it till the time the error is decreasing. Once the error stops decreasing, or once it plateaus out, that when you go from this epoch to this epoch, it's not reducing much, then you stop it. But here, since this is a tutorial, we have set the number of epochs to 15. And I've set a low enough learning rate, and my batch size is 100, and display step here basically says after how many steps you want to display your plot, right? So after every epoch, right, I want to display my values. So that's what this display step basically means. It's basically the number of steps or the number of epochs after which you want to keep showcasing or displaying this plot. Okay, so this is the initialization. Now once the initialization is done, see, look at it, what all have you initialized? This is very important. Okay, we got our data set first, right? Next, we initialize some plotting tools, then we initialize the network parameters, placeholders, right? And then weight initialization, and then the parameters for the optimization. right? So bunch of steps here, and you need to remember all these steps and not forget any of them. I've seen cases where some of our students, including myself, when I was learning it, I would forget to do weight initialization and everything goes bonkers. Okay, you have to be careful not to miss any of these key steps. Okay, in the next video, we'll see a very simple model using sigmoidal units.